Hey, what's up, guys? Yeah, welcome to my video. So, previous that I think so in this video that we're keep proving the IP equal to PSPACE, and so previous we just proved that sharp set, or basically the sharpie is the subset of IP. Just by proving the idea is very novel. Right, it's basically replace, so you can replace Boolean circuits to build a polynomial. So it's the optimization. So for example, if you have AND, then you can just replace by x1 times x2, and then you have OR, then you can just replace by this. Okay, so the sharp set become like, if you want to start with this Boolean formula that they say is that 3C and F. So if you force to be 3C and F, then you can just try to compute this. Okay, so once you write the polynomial representation of this, then the Merlin just try to convince Arthur that this sum is k. Then what Merlin did is just send this polynomial. Let's call this polynomial p of x1, and then send this polynomial to Arthur, and Arthur can just easily verify p of 0 plus p of 1 is k. Otherwise, that Arthur reject, and then Arthur just randomly pick A, right, belongs to the finite field f of p, and then define this to be p of A. Then the problem becomes like a mathematical induction. Okay, and the proof idea is that in every step, right? So in every step, and let's say the degree m of d, right? So so every step your polynomial, let's say degree m of d, right? But obviously that this polynomial, right? This polynomial at most degree x3m, right? For each step, right? So so your d, right? Every step that the author will reject in probability 1 minus d divided by p, right? Because the degree d polynomial in finite field at most have d roots. Okay, and then you just take, so the total probability that if Merlin want to treat with author, then the author reject with probability at least greater or equal to 1 minus d divided by p n. So this is union bound, right? Because the previous algorithm will finish in n steps. Okay, so you just that, and then you know d is 3m, right? So however, right, d is just at most poly n. Okay, and the p is just 2 to p can be said to be greater than 2 to n. So as the n goes to infinity, then you know that this 1 minus d divided by p to n will approach to 1. And if this is true, then by your calculus, you know that when n large enough, then this 1 minus d divided by p to the n will like arbitrarily close to 1. Okay, so let's say can be greater than equal to 2 divided by 2/3. Okay, so this is the proof. This is the sharp set equals to IP, a subset of IP. Okay, so once you have this, then it seems like everything's simple, right? Because you just replace these to be TQBF, right? So for example, TQBF basically there is this x1, for x2 is this x3. So these are Boolean variables such that phi x1 xn is true. Okay, so we can do the optimization, right? But we already have this exist, right? It is just sum. Okay, so this is sum. So idea is simple, right? For all should replace by product. Okay, this is super trivial, right? Because for example, if I want to say for all phi of x1 of the xn, then I can replace to be product, right, of x2 belongs to 0, 1, and the phi of x1 0 xn, phi of x1 1 xn, right? So in order to sorry, just by this, right? Because if for every x2 is 1, then this must be 1 times 1. Okay, so simply speaking, that you just replace for all to be the product. Okay, so exist replaced by sum, and for all replaced by product. Okay, this is similar as previous. Okay, but right, so okay, so the idea is that okay, so now you have this. Okay, so you can just simply replace everything, right? So okay, so there is a right, so let me just use products. This is products, and this is sum, just for convenience. Okay, so now you can arrive a large, very large guy, right, which is sum x1 0 1 product x2 0 1 and the sum of x1 x3 0 1. Okay, so let's imagine that the final guy's product is for all. Okay, actually this doesn't matter. Okay, so you can change this to be product xn products xn 0 1 and yeah, phi of x1 xn. Oh, then you want to convince. So Arthur want to convey. Merlin want to convince Arthur that this guy is wrong. Okay, so yeah, that's it. Okay, but the problem is that every time you right, so and you might think that, oh, can use the previous method, right? I can just strip this and say these guys. I can just send this point. Merlin can send this polynomial to Arthur and then just strip. Okay. But the problem is that since there's a product, right? So sum will not add a degree, but product will, right? So so you might have total like maybe n of this product, right? So this polynomial, let's say this p of 1, may have the 2 to the n times 3n. So this is degree. P may have degree 2 to the n times 3n, right? Because every time you have products, then you degree will multiply by 2, right? So 2. Right? So you have 2 to the n 3n. Okay. Okay, so now the problem is that Merlin cannot just write down this all the numbers to Arthur, right? Because Arthur is the polynomial guy. Arthur don't have enough time to read this p. Okay, so the trick is just using the linearization. I think this is a very interesting idea. So very simple is that we only care about xi in 0 and 1, right? So in this case, that xi to the k is xi, right? For every k greater or equal to 1. Okay, so once I have this, then I can define maybe Rxi to be a linearization. So simply speaking, Rxi just informally just replace Si to the k to Xi. So whenever I say Xi to the k, I just replace Xi. Okay, for example, if I have some polynomial like this, let's say x1 to the 5, x2 to the 4th, plus x1 to the 6, plus x1 7, x2. Okay, I can just linear after our linearization, then this guy be x1, x2 plus x1 plus x1, x2 to become x1 plus 2, x1, x2. Okay, you can just simply use. Okay. So once you do this, then all you need to do is just you are trying to prove this. Right? You're just to okay. So this is 0, 1, and this is R1, and the product of x2. So let me just for let's see, I still write Rx1, x2. Because every step I need to linearize, okay? And keep going, x3, 0, 1, rx1, rx2, rx3, and keep going until that the xn, 0, 1, r of x1, r of xn, and the phi of x1, x2 up to xn. Okay, so now this will, after all this, right, this degree, so every xi is, right, so this is linearization. Right, so you almost have x1 up to xn. Okay, so for given any variable, the degree at most 1. Okay, so this Rx will kill degree, and the product will enlarge the degree, but still that will keep going. Okay, so you can check that this is this now every step you at most have polynomial degree. Okay. Okay, so in principle, this is the okay. because now obviously that hopefully you can use the previous idea, right? You can first strip this. You can first define, say, this guy as P of x1, right? So you get P of x1, and then you're just using the same thing, okay? And you just keep going, okay? So merging, okay, so let me just maybe do, so there, now we have three of case, right? So we have three cases. The first case is that author want to convince that the first case is that author want to convince, the merging want to convince author that merging want to convince author something is true, but the first symbol, right? So you can see this formula, right? We have three cases, right? We have these cases, and these cases. It's not like in a three sets, right? We only have in a set formula we only have some, right? But in this case we have three cases. So case one is this, right? So case one is that there are some formula. Let's call this formula VK, okay? And this VK equals to some products. Maybe I don't know, right? Let's call VK. Maybe it's XI, and there's RX1 . Okay, and sum of XI plus 1, and maybe a product of XN, and then there's RX1 of RXN, and there's a phi. Okay, so phi total have n in the formula, but let's say this is R1, Ri minus 1, and the Xi, Xn. Okay, so this is maybe some step that Bernie want to convince Arthur that VK is equal to this. Okay, so the first symbol here is a product. Okay. Okay, so now it's very simple, right? So now that the Arthur Merlin just send this polynomial to Arthur, right? It's PXI. Okay, so Merlin so it's just the same as this, right? Merlin sends P of xi. By the way, P of PXI as xi at most have what? At most have linear, right? So it's these guys is degree 1. Okay, because right, because in every step, right, you always linearize. So maybe in the middle step that you already linearize xi. So this guy's linear axi plus b. Okay, the rest are just a number. Okay. So Merlin sends pxi degree 1 to Arthur. And so Arthur check. So Arthur can check. Because Merlin say this is true, right? So Merlin so Arthur can compute this. Right? Arthur can compute whether this is true or not. Okay. Arthur equals to VK. Okay. So Merlin can convince Arthur can just check this. Okay. And then the same thing happens right? If Arthur is cheating. Yeah, if Merlin is cheating, then there will just be 1 over P probability. So the success probability for Merlin cheat Arthur is just 1 over P, which is very small because it's degree 1. Okay. And then Arthur just randomly, then the Arthur just pick. Let's say A belongs to FP, and then P of A, and just become the next step. Okay. And then the case 2, which is case 2, is just sum, right? So or basically in our notation is this. So this is similar as sharp set. Okay, so it's that's important. And there's a case 3. Okay, so case 3 is that let's say VK is basically RX1 maybe RSI to something XN, RX1, RXN, and phi. Okay, so it's R1 up to RJ and XJ plus 1 XN. Okay, so in this case, J is greater than I. Okay, so this is the middle step. That's third case, right? There's a linearization. Okay, so the idea is that you can still do the same thing, right? Just copy this and collect it. Call this guy as P of xi. Right, but in this case, that xi may not get linearized, right? So P of xi at most have degree. Let's say 3m. Okay, you can check this because P of xi doesn't, although it doesn't xi, right? But in the previous step, we still have some xi. Okay, so P of xi must have degree 3m, right? Because yeah. Okay, so you can prove that in this case that the cheating probability so the cheating probability at most like d divided by p. So d is at most 3m. Okay, so the total error that one can do some total error. Okay, so total error is basically this. So each of these and this will correspond to 1 over p, as I just said. Okay, and finally, right? Final have rx1, rx2 up to rxn. Have error at most 3m divided by p. Okay, and then the rest, right? The rest, the reducing operator I have error like 2 divided by p. Okay, so you can compute total. Right? You can compute totally the probability. I mean, it's basically n divided by p. Because you at most have n of it, right? Plus 3n divided by p times n. Because each of them is at most 3n divided by p plus 2 divided by p. And then you total have what? N squared, right? N squared. You have I from 1, I minus 2, right? Because you have like n squared rxi. Right? So these guys are 1 n squared. But it doesn't matter, right? This is just poly n divided by p. Where p is like 2 greater than 2 to the n. So you can make the total error like very small if n is large enough. Okay, so the idea basically is the linearization, and you can use the same idea to prove that TQBF is in IP. Okay, so once you prove this, then you arrive that TQBF is in IP. Okay, but then previous that we proved that IP is subset of PSPACE, then combine this, we also know that TQBF is PSPACE complete. Okay, so we should arrive that IP equals to PSPACE. I think this is a very beautiful proof. See you guys next videos.